I'm David Culler, Faculty Director for I4 Energy. We have much of the rest of the crew here. So let me welcome you and those of you that are out there in the rest of the world. I think we have pretty good coverage. So it's my pleasure to introduce Jay Taneja, today's speaker. And we're doing a little bit of double duty here. As part of graduate division, we also have a requirement for a thesis defense, which we turn into a PhD seminar. So that means that at the end of this, you get to ask those really hard questions. I'm sure Jay will appreciate that. Which is to say, Jay's at the end of his graduate career here, has been engaged in quite a wide variety of projects, started with network-embedded systems technology, and has reached out into really interesting work far afield from that in the developing world and issues of using some of that technology for sanitation and other work. So has worked with a tremendous number of people across campus, the Keck HYDROWatch project, and is now in the finishing stretches. And often students that are in this, there's also this notion that they're out hunting for jobs. In Jay's case, that's not the case. He's made his decisions, and really quite interesting. He's going to work for IBM. That may not surprise you, but in Nigeria. No. Kenya. Well, there you go. So, Jay.
All right, how's my mic? Can everybody hear me? Great. Well, thank you all for attending today, to you guys here and to everybody on the web and other campuses. So I'll be talking today about supply following electricity loads and the potential for their role in future electricity grids. So to kind of begin, there's a report that was put out by the California Council on Science and Technology looking at the role of energy in our future. It projects out to 2050, and there's a few pieces of legislation and policy that kind of guide this this process of getting to a sustainable energy future. So among those, many states, and California in particular, have put renewables portfolio standards in place, where they're pushing to have 33% of our renewable electricity, or of our electricity, be provided by renewable sources by 2020. And as well, we've got some emissions goals in place. So by 2020, also, there's legislation that aims to push for 1990 levels of emissions by that date. And then further on, by 2050, we want to cut to 80% below those levels. What does this report say? Well, the good news is that we can get to these aggressive targets. It's possible with some of the technologies we have in place and some of the technologies that are in the pipe. But further, the report kind of documents that we have about 60% of the technologies that are already things we know about, and that they're things that we can easily not easily, that we can scale in order to get to this level. But the remaining two big technology limitations are decarbonizing fuel, and then the second, which is electrical load balancing without emissions. And the idea here is you want to be able to maintain a match on the grid between supply and demand without any additional emissions from causing that. And just from our from my studies so far, if we were to reach this 33% renewable and provide the firming required to flatten those renewables with natural gas, we would be well past our 2050 target already, just on the 33% of the grid, not to mention the remaining two-thirds of the grid that we need to provide. So how do we get there? Well, right now the grid tends to be composed of what are called baseline and dispatchable sources. Baseline sources, things that don't generally turn off, that you leave on the entire time, things like coal plants, nuclear plants that just produce a constant amount of energy, and it's very expensive to turn them off. And then these dispatchable sources, things that you can turn on and off and control their generation in order to change the amount of electricity produced. So these are things like natural gas plants generally. And then on the other side, the balance side, the load side, you have oblivious loads, things that are just operating on their own control loops or when people request them on demand. So all of our industrial, commercial, residential loads generally tend to fall into this oblivious case where they're just consuming based on a pattern. And the communication generally goes one way, in that the grid is just looking at what the loads are consuming and kind of predicting that, and then changing its set of generation accordingly. So what's changing? Well, as we add a lot more of these what's called non-dispatchable sources, things that are not able to be directly controlled, so you can't control how much the sun shines or the wind blows. You can just turn them off or on, basically, the generation sources. As these begin to become more prevalent on the grid, you get larger fluctuations in the supply side. And so there's a few ways you can deal with that, but what we propose essentially is this new class of loads called supply-following loads, loads that are able to kind of alter their consumption via communication with the grid and then communication from the grid in order to decide how they should alter their consumption. So from a utility or grid operator perspective, this is the most famous curve in that world. And what this is called a load duration curve. And it's essentially a statistical characterization of how much load there is on the grid over the hours of a time period. So, for example, a year. And so it's essentially a cumulative distribution function that lets you know essentially how many hours are at each level of consumption over the year. So what's striking about this load duration curve is that at the top there's a pretty nasty peak. And this peak is essentially saying that for a very small number of hours of the year, you're using resources that aren't used any other time during the year. And if you break down the types of sources that are used, those tend to be the sources that are peaker plants. And those peaker plants are generally the most expensive to operate, or else you'd be using them at other points in the electricity grid. And they tend to have the highest emissions. They tend to be the lowest cost capital expenditure, but the highest operating expenditure for utilities. So that's why they maintain their role as peaker capacity. So it's said that utilities generally spend somewhere on the order of 10% of their generation capital on providing this last 1% of load up here right at the very peak. So it's a very inefficient part of the curve. So how is this generally dealt with? So there's the field of demand response that's been documented in I4Energy talks, and there's a great research center at LBL, and they're doing fantastic work. And their goal there is to essentially incentivize reduced loads during times of peak demand. So they're trying to get consumers of electricity, and generally it's large consumers that they can either phone up, or they're starting to work on automatic ways to do this at scale in order to cut demand at those peak times. Maybe in California, these times tend to occur in the middle of summer when there's cooling load from air conditioning in the Central Valley. So beyond that is demand-side management. This is essentially trying to shift demand not just at these peaks, but also it's trying to shift it to other places on the duration curve. So it's not just trying to curtail like demand responses, but it's actually trying to relocate that. And then the set of techniques we're espousing here is supply following. So actually having these collections of loads that are able to alter their consumption based on a few different characteristics. You look specifically at power proportionality of the loads, how much they're able to change their consumption to reflect the actual work done, as well as exploiting the slack in their load profiles. How flexible are the loads in order to shift and schedule consumption to kind of better, to make this duration curve a little bit more tractable for a utility to manage. So the idea with supply following is that you're not just trying to cut off the peak, you're actually trying to relocate that consumption to elsewhere. So you're essentially tipping the balance of this curve so that the energy does still get consumed, but it gets consumed elsewhere. So that's where it's different than things like energy efficiency. So as David explained, this is a dissertation talk for me. And so as part of that, I wanted to lay out some of the key questions that my dissertation answers. Now, I have 5 questions up here, but and they're all quite a bit of graphs and other things I can show you, so I don't want to spend 4 hours up here boring you guys. So in this talk today, I'll focus on two of these questions. So one, we'll talk about to what extent supply-following loads can actually help the match between supply and demand. And the other is, how can we actually make existing loads become supply-following? How can we alter loads' consumption patterns to have this nice quality? The other questions I'll address, but only tangentially. If you actually want answers to those questions, you will need to read the dissertation to find out. Great. So jumping right into how the talk is arranged, this is an outline of what I'll be discussing today. So I'll begin by looking at modeling electricity grids. In order to really understand the role of supply following loads, we need to understand how they work in a broader context. So we actually look at a few different electricity grids to understand. We move on to a specific case study looking at the California electricity grid at 60% renewables. And then we move into the more micro side of things. We actually take a few different supply following loads, and I'll discuss how we implemented these as well as how they perform their task of supply following. And last, we'll look at some other strategies to improve the match between supply and demand. So the California ISO and the California Energy Commission provide a really nice couple of data sets that allow us to kind of understand grid operation on an hourly basis. So this chart represents a year's worth of data of the California electricity grid, and on an hourly basis we know how the breakdown is of generation energy between 10 different kinds of electricity sources, all listed up here in the top right. And among these 10 kinds, there's a few things that jump out, but what I'll point out first is that this chart is a chart of daily averages. So you're not going to see some of the very peaky behavior that happens during the day. The graph would get too noisy if we represented it that way. But you can see some statistics about what actually happens. So we peak out around 47 gigawatts. We average around 26 gigawatts in California. But what's striking about this graph is that about 60% of our electricity is in these top two categories, the gray, which represents imported energy, and the dark red, which represents thermal energy. It's listed as thermal. It's primarily natural gas facilities, so those dispatchable facilities that are turning on and off every day. Everything else you see weekly variations with demand. That's what each of these spikes in the overall demand curve mean. You see seasonal variations. Hydro shows quite a bit of seasonal variation. It's highest in the spring and early summer. And then nuclear is generally entirely flat. That's baseload capacity that's only turned off generally for maintenance or other larger concerns, as we're seeing now. So how does this compare to other electricity grids? In the dissertation, I look at three different grids. I look at Germany, which Germany has a far more renewable grid than California does nowadays. It's already at 22% renewable as compared to around 10% for California. But it also uses about 44% coal. And this chart represents the German grid. The top category is actually everything besides wind and solar. So that's not represented on this chart. But as well in Germany, the reason for some of this is that solar has actually been heavily subsidized by the government. And what that results in is that 50% of the renewable investment actually goes to about 20% of the renewable energy. That's the solar portion of the grid, to much consternation of other renewables stakeholders in Germany. As well, Germany has some other considerations like a nuclear phase-out that they're planning to finish by 2022, which will exacerbate the need for some sort of, in addition to renewables, but also techniques to manage those renewables. Another grid we looked at was Ontario. Ontario is actually quite a different situation because they already have primarily carbon-free generation. They get 78% of their generation from hydro and from nuclear sources, and only a small amount, the remaining 3%, about a gigawatt and a half of wind capacity. And there's no utility-scale solar in Ontario. So one of the things I'm answering is whether it actually, how these decisions came about and whether they make sense from an energy perspective, regardless of the actual policy concerned of, for example, not having any utility-scale solar. As well, it's important to note the behavior of this nuclear proportion. If you look at it on an hourly basis, again, this is a graph of daily averages. If you look at it on an hourly basis, nuclear on some days actually provides close to 80% of the generation for some hours. And that's important because you can imagine that if you're able to make other loads more efficient, or you have to cut back, or you try and increase your nuclear proportion, you might have times where it's required that you turn off nuclear plants, and that's very bad for the operation model of nuclear plants and for the economics. So what we might see as we get rid of some of the remaining fossil fuels on this grid is quite a change in its generation mix. So we'll drill in a little bit to California to understand some of the implications of going to higher levels of renewables. And so the experiment we wanted to undertake here was looking at renewables in the behavior of the electricity grid at a far more renewable level. So not just the 33% we're looking at in 2020, but going well beyond that. So we targeted 60%. And the reason for 60% is that's when you start to see really interesting behavior. And as well, we see that the importance of techniques like demand response and demand-side management and supply-following loads really increase as the penetration goes up. So we aim to look at a grid that was 60% renewable. So in order to do a study like this, we had to make a number of assumptions. Among those, we maintain the existing population of wind and solar facilities, and we just scale up their consumption proportionally, or sorry, their generation proportionally. And what that essentially does is it maintains the same temporal and weather patterns that affect the production of generation, and all we do to size them is figure out essentially what size we would need for a specific proportion of renewable energy, and then we try and minimize the total capacity of resources needed to get there. And essentially that's some measure attempting to minimize the cost of what it would take to have 60% renewables. As we increase those renewables, what we're also doing is we're displacing other energy sources. So the order we've chosen to do that is to first displace imported energy and then displace thermal natural gas generation to get there. And so what happens is at times when there's renewable electricity production beyond the reference demand that we're using from our current demand, we have excess electricity. And you'll see in the next chart about how that operates. We're not considering any additional energy storage yet beyond what's on the grid now. As well, we're not worrying about transmission constraints at this stage of the study. So this is the same chart I showed you earlier, the current California grid, but notice how this changes as we ramp up to 60% renewable. So this is the same grid, except we've now really increased the solar and wind by going from about 3.5 gigawatts to about 87 gigawatts of capacity of solar and wind. And we've displaced a lot of the thermal and imported generation. We now have somewhere in the neighborhood of 10 or 11% thermal and imported generation. We didn't alter the hydro and the nuclear and other baseload elements in doing this analysis. So a few things jump out immediately when you look at this graph. One, right now we're operating mostly in a situation where we're concerned about summer in the current grid today. And because that's when our peak load occurs, and that's when we need to use the most of our resources. In this situation, that's no longer the case. We no longer have that cooling crunch in the middle of the summer when everybody's turning on the air conditioners, because just as nature intended, that's when energy is most abundant. That's when the sun is shining its brightest. There's a lot of wind energy available, and that's when we have copious amounts of excess. But at the same time, what we also see is that winter becomes the toughest in this scenario, because the change in available energy from the environment is much larger than the change that is shown in demand. We actually end up using a lot of our fuel reserves in the winter. So this is when we're turning on our natural gas plants and really aggressively using our fuel resource. But on the periphery of that, what we see is that in these kind of shoulder seasons, we have this intermittent excess and deficit that we could use some techniques, some load shifting techniques and some supply shifting techniques to kind of address the situation where we're excess in the middle of the day and then deficit at night. So what does that actually look like? This is a 5-day period in the autumn season, and it shows that pattern I just described of having excess in the middle of the day when there's a lot of solar electricity available, and then deficit in the middle of the night. And so you can see that at some points, like on this third day, there's quite a bit of deficit that we end up dipping into our thermal resource as well as our imported resource in order to meet demand, this reference black demand. So how could we imagine dealing with this and trying to improve the match between supply and demand, and as well as cut down on emissions? So first we could imagine using some of our supply-side resources. So we see this hydro resource, this blue resource here at the bottom, and its current management results in it generally matching the overall demand curve, this black line. The shape of it is very similar to the hydro, and that's a reflection of how these resources are managed now. We can imagine that since our goal is no longer to match demand because we have excesses at some times, it could be an altered goal to try and displace our fossil fuel needs at other times of day. So we can imagine managing this resource differently, and I'll come back to that later. Another solution we can imagine is targeting our efficiency. So there's all sorts of work going on energy efficiency. It's an age-old topic, and it's one that is critically important to improving this match, but we can target which types of energy efficiency we perform. What classes of loads make sense? Which loads are the ones that are consuming energy in these times of deficit? Next, we can imagine utility-scale energy storage, and this is one that has been held up for a long time, and there's lots of of great research on the topic, but it still hasn't grown to large utility scale yet. But in this, essentially what you're doing is you're shifting periods of excess supply into times where you might have deficits. So you can imagine taking each of these green excess peaks and pushing them down into the valleys when we're using fossil fuels otherwise, with large reservoirs of storage. And last, you can imagine energy shifting. And what the value is here is you can actually shift in both directions. You can take load from times where you would have been consuming fossil energy and move it to times where you have excess energy available. You can advance it, so you run it earlier than it normally would have, or you can delay it and you run it later than it actually would have. And so this is the one we'll dig into first. So now that we have kind of a grid perspective of what's going on, I'm going to jump into a micro perspective and look at what actually happens with supply following loads and how we can implement them and understand their performance. So as part of the study, we've implemented 3 supply following loads. But there's some considerations that are important when looking at what it means to make a load supply following. So some of the key ideas here are looking at agility, looking at how quickly the load can change its consumption. And that, if you think of it as the notion of a battery, it essentially reflects power delivery and frequency of operation. So how often you can use that electricity load. The other one is proportionality. So this is essentially categorizing how well a load reflects its consumption reflects how much work is done. And so loads that don't change from day to night, like a building heating or air conditioning system that doesn't change its consumption much from day to night, is said to be not very power proportional. But if it were able to change its consumption largely, then it would be quite power proportional. And so what this power proportionality quality represents, this characteristic, is that it shows how much you can flex that load, how much slack there is in that load's temporal profile. So in cataloging each of these 3 supply following loads that I've built, we look at improving the performance of the device for supply following using kind of 3 main techniques. One is adding communication so that the load is aware of what's going on outside of its local operation. We add infrastructure equipment so that it's able to be more supply following. And then last, we imagine using advanced controls and how we can just change the software around how a load operates in order to change its load consumption behavior. And we can imagine using families of these techniques all together. So the first supply following load that I'll introduce is actually a heater. And this is a empirical model. That is, there was a cycle of a heater in my advisor's home that I used the data for to understand the temperature behavior. And this is top plot, and then the power behavior. And we use that cycle to build a model so that we can alter its operation and understand how it might change its consumption accordingly. In the third row here, we're looking at slack. This is essentially an energy measure of how much flexibility there is at any point in its operating pattern. And this has to do with some of the constraints in the control of the device. So you can see in this top chart, there's a temperature boundary or a temperature band, a guard band that we're trying to maintain. And as you traverse through that guard band, the slack available to you changes. And on this last pane is a wind trace that's sized to provide 50% of the energy that would be needed by this heater. And in this first column, these are all. This is an oblivious load. So this load isn't considering what's going on the supply. And on this bottom graph, it's just operating given its local constraints. So the next column represents a supply following load that we call supercooling. And essentially what it's doing is it's widening the guard band so that in periods where there is a deficit of renewable electricity, and you notice now in this bottom chart we've added a red dashed line. When we're below that threshold in supply, we change the operation so that we allow the room to get cooler. We allow it to naturally cool for longer. And that allows us to limit the number of cycles that occur in those times. And so we have periods of more dense activity and periods of more sparse activity. And these cycles, though fewer, tend to be a little bit longer. We also see that during those times, we increase our slack so that we're able to traverse a larger amount of flexed energy. And the third strategy we tried is what we call a wide guard band supply following strategy. And it takes the same principle on the lower edge of the guard band as the previous, but it also increases the higher edge of the guard band. And what that essentially says is that when there are periods of excess in the wind in this bottom chart, you operate by letting the heater run for longer. And so you oscillate from having situations where you run the heater run for longer to where you try and avoid using the heater. And that results in having that increased slack kind of, it changes the slack portfolio, and it actually makes the cycles a lot more sparse relative to the operation of the other refrigerators. So how does this fridge perform? What we see here is a breakdown of the energy, and what jumps out immediately is that the supply filling refrigerators actually reduce consumption quite a bit. And the reason for that is that you're not providing the same level of service. By widening the guard band, just as we see in buildings, and the Center for the Built Environment has talked about for many years, you can widen the guard band, reduce the level of service somewhat, and really save a lot of energy. But that's not what's critically important here. What we're looking to do is manage this breakdown. So this is a breakdown between renewable and non-renewable energy. And in our oblivious case, like I said, it was sized to provide 50% of the energy from our wind turbine. In the supercooling case, we're actually able to provide 60% of our energy from the renewable attached renewable source, and slightly less in the wide guard band case. And why that's actually slightly less is that as you run the heater for longer, so in those periods where you're running the heater for an extended amount of time, it runs more efficiently and it changes the temperature more efficiently. So by actually running more cycles in those times, when in the supercooling case, you're able to consume more electricity during the renewable case, and that makes this balance shift slightly more towards the renewable side in the supercooling case than it would in the wide guard band case. But that's still not the most important thing here. So this is a fairly modest gain. It's only 10% relative to the oblivious case. But when you think about the energy consumption pattern of these devices, it's fairly spiky. And so what happens is that by having these spikes of fridges using power, and imagining if you have other fridges doing the exact same thing, you get this very nice statistical multiplexing behavior. And so what's happening here is we actually started with a different assumption. Instead of 50% of the electricity, there's only 25% of the electricity. So this leftmost bar here on the chart represents that 25% of the electricity of the device. And I should note, I switched here to refrigerators instead of heaters. The study uses similar models for both, but we modeled the population using refrigerators. The same conclusions hold true for the heater as well. But we provide 25% of the electricity of the device using renewable sources instead of 50 as in the previous example. But as we add fridges with their associated 25% renewable sources, that statistical multiplexing, allowing these spikes to kind of fall at different times, allows you to, as a population, use a far more renewable proportion of electricity. So you get up to levels where you're using over 80% of your electricity is coming from renewable sources with just as few as 10 of these devices. And so this really works well when you have these spiky profiles of consumption. But what's also important to notice here is that there's no actual direct communication or coordination among these fridges. They're all looking at signals from the grid and deciding how they should consume their electricity accordingly. So there's no actual communication. It's just one-way communication with a little bit of information technology added on to the control of the device. So our next supply following load is what we notice is that in our refrigerator case, there isn't very much thermal storage. There isn't very much slack that's provided by these loads. If you change the consumption pattern of a normal refrigerator, you can't change it by more than a few minutes without reaching your edge of your guard band and having to consume electricity again. And so what we aim to do with this is actually improve the thermal storage characteristics of a refrigerator. And so looking at the operation of a refrigerator, and this is empirical data from a refrigerator that is a typical refrigerator that would be found in a residential setting. What we see on the top chart is temperature of the refrigerator compartment in black and the freezer compartment in black and the refrigerator compartment in blue. And in the middle, that spike is actually the defrost cycle. They generally tend to happen once or twice a day, depending on the device, and it's meant to remove frost from the evaporator coil. And on the bottom chart, we see the power of the entire unit. And you see on that on the defrost cycle, there's quite a bit more power used, but it's for a very short amount of time. but generally the cycles are fairly regular. So this is the operation of a normal refrigerator, unmodified, and you'll see that it uses about 77 watts in its steady state power. And remember that number, we'll come back to it in just a bit. So the way we actually altered a refrigerator was to add a thermal storage element to the freezer. And so this is a picture of the freezer of the device, and you'll see this. It's a prototype, so there's lots of wires and lots of communication and sensors and other things. But what we've added here is actually a thermal storage element, and this is essentially a tank. It's a stainless steel tank that has a phase change material in it. And what's really important is that this phase change material, it's specifically chosen. It's this ammonium chloride at a specific concentration such that it freezes at around minus 15.5 degrees Celsius. And so what the freezer operation is, it actually generally runs below that level, below minus 15.5 degrees Celsius, so that in the operation, it's constantly frozen. But if we want to melt that device, we just cut off the power from the compressor, and we allow the heat to be captured by the ice battery, and so we don't allow the air temperature in the freezer to actually increase. And so there's roughly 6 kilograms of salt in solution inside these 3 tanks. As well, beyond that, we have tubing, and this tubing, since we're cutting off the power to the compressor, we're actually also cutting off the fan that blows air from the freezer to the refrigerator. And so what essentially is happening is we need something to be able to remove heat from the refrigerator. So we have this tubing that runs through the tanks as well as through the refrigerator compartment, and it's connected to a pump that's outside. And this tubing allows you to remove heat from the refrigerator. Inside the tubing is a propylene glycol-based solution that freezes at a level like minus 35 degrees Celsius. So it's not going to freeze in our normal operation. It allows us to remove heat from the refrigerator compartment. And last, we have a fan that helps with convection so that we get nicer freezing and melting properties inside our freezer. So I want to stress that as this is a prototype, this isn't exactly how you'd build it. You wouldn't cut down on space in the freezer. You'd probably integrate these things into the actual commodity device, the refrigerator. But for the sake of proof of concept, we've tested and run with this operation. So what does it look like? Well, this is the operation of a thermal storage refrigerator. It's the same chart as before, so it's over a fridge operation over a day, but there's now a new line. And this black line here represents the temperature of the thermal storage element, the ice battery as we call it. And what you see about it is that since it's a larger thermal mass, it doesn't oscillate as much as the air in the freezer. So the oscillations per cycle are much smaller. As well, that minus 15.5 degrees Celsius freezing point, phase change point that occurs, it actually asymptotically approaches it while the ice battery is absorbing energy. And what's also important is that you see that the temperature changes quite quickly in the regime below minus 15.5 degrees. That's sensible heat. That's just the result of the delta T, the change in temperature. But the phase change, the heat involved in the phase change, is actually much larger. So you're able to capture quite a bit more energy going across this phase change boundary. And that's why it's critically important that we use a phase change material there. What we also see is that the steady state average power is increased by about 10 watts. It went from 77 earlier in the non-modified case to 87 watts in this case. So it's about a 13% increase. We imagine that if we actually commoditize this design, it would be quite a bit lower. We'd be able to get it close. We'd use a better pump and a better fan, lower power that would be sized correctly, more appropriately, and be able to kind of get this number closer to the operation of the normal refrigerator. So how does this perform in a supply following case? So this is a chart that shows 3 days of operation of this fridge operating in supply following mode. And what that means is that it's the same chart as before with temperature on top and power below it. But then below that, we actually have a supply powered signal from the California ISO. And this is actually the total number of renewables that are available in California. So you can see oscillate from anywhere from about 2,500 to 3 gigawatts, all the way up to almost 6 gigawatts at its peak. And each of the colors here represents different states. So all we're doing is a very simple threshold. So we have a state where there's low renewable power availability in red, medium power availability in tan, and then high power availability in green. And each of these states, the fridge is actually, the control algorithm we use is different. So in the low power availability case, we're trying to avoid power consumption. So we actually maintain a higher temperature guard band. And what that allows us to do, as you can see, for example, the last pane here. What that allows us to do is melt the ice battery in order to provide that same cooling functionality that the compressor would provide otherwise. And essentially, it makes us require fewer compressor cycles during that period. In the medium availability case, we just operate the fridge as it would normally alter, so we don't change its control pattern. And in the high availability case, this green case, we keep a tighter guard band. And what that essentially causes is more consumption so that we charge the battery somewhat faster when there's a surplus of renewables available. So you see there's quite a larger number of cycles that occur in these periods when there's high renewable availability. And so what the result of this is we get this kind of stratified operation between a low supply, medium supply, and high supply, anywhere from 50 watts to about 80 watts. And that allows us to imagine that this fridge, or we can see that this fridge, based on this situation on the grid, can change its consumption. We imagine that if we changed what these three techniques were, we could get that to stratify even more. What you see about this not matching our 87 watt, the medium case not matching our 87 watt steady state, is because we're constantly shifting between states here, and so you have some resultant effect from the previous state you were in prior, so you don't match up exactly with steady state in each case. And so the next question that we sought to answer was essentially, what can we do now that we have these supply following refrigerators? What would they look like over the scale of the entire grid? And so this slide attempts to answer that by looking at the duration curve. And this is the same idea of duration curve as last time, but it's the difference here is that instead of looking at overall demand, we're now looking at just the natural gas proportion of the supply mix. And specifically, we're now looking at a penetration of the supply-following fridges in California. So this is the base case. This is, again, our 60% renewable grid. And this is the natural gas duration curve. So this is when there's no supply-following refrigerators. What we can see is that now 65% of the time, the natural gas generation is not used. So that's what this point at on the x-axis represents. But we have this nasty curve at the far left, just like we did with overall demand. Here it might be even nastier. For the top category, 9 hours of the year, we're using almost 3 gigawatts of capacity, which is 15% of our overall capacity for 9 hours of the year in this case. And so what we'd like to do with our supply-following fridges is actually target that max and try and bring down that peak. But it's not the max of the overall load duration curve. Now it's the max of specifically the natural gas generators. So we can run those generators much more cleanly from a utility perspective. So what happens when we have 10% of our refrigerators running operating in a supply-following mode? So what we're really looking at, again, is this peak here. So we'll zoom into that peak. And when we have 10% of our refrigerators operate that load, what we're able to do is kind of pull down this duration curve towards lower consumption and less hours. And what that essentially results in is about 900 megawatts of peak capacity. That's almost a nuclear reactor being shaved off the top just by having 10% of the refrigerators in California use this supply following technique. And it's relatively cheap materials and everything else. So as you amp up and you get to 50% and 100%, what you start getting is 2-3 gigawatts. These are large numbers from just changing refrigerators over to being supply following, as well as you could imagine using this supply following technique in addition to other techniques like demand response. If you could shave off the top 9 hours, in this case, using a different technique, you could get down to 15.5 gigawatts, and that would be a full 4 gigawatts, a full 20% of the original capacity you needed just by employing these two techniques across the grid. So our final supply following load that I'll document is a living laboratory air conditioner. And what's important here is we took a computer lab. This is actually a computer lab that's in Corey Hall. It's the first floor of Corey Hall, 199, and it's an undergraduate computing lab, so it's used mostly for homework. There are occasional classes held there, but it's used very intermittently, and it changes throughout the term. It's got roughly 15 or so computer terminals, and what we added to it was a networked thermostat. So we changed the thermostat so that it was something that we could actuate remotely, and we built a model of how the cooling and heating dynamics in this room work as well as building a system that allowed us to run a control algorithm elsewhere and change the operation of the thermostat so that it's changing the operation of the air conditioner accordingly. So to use this, we use this to build this. We use this SMAP system that I believe there's been an i4Energy talk before about SMAP, and this is essentially a data warehouse, a way to kind of fuse all different kinds of data sources in order to kind of run applications and make use of energy data. In this case, we use energy data, weather forecast data, in order to make decisions in our control algorithm that affect the operation of the heating and cooling system in this room. So what's important in energy efficient HVAC is that you actually have this kind of uncertain heating load that's caused by the presence of equipment that's changing its power consumption based on whether people are using it or not, and then the people themselves coming in. We're all 75-watt light bulbs, so we're all consuming some amount of power. We're creating some amount of heat accordingly, and that heat is reflected in how the operation of the room goes. So what you see here is about a day's trace of the temperature in the room, and you can see that there's two salient features here. One, that there are these dashed lines that you can barely see on the projector that essentially it's trying to maintain the temperature between those two dashed lines. That's the guard band of the room, but it's often overshooting it. So many times when the compressor turns on, it stays on and it pulls the temperature well below our lower threshold, which is at around 22.4 degrees Celsius. As well, what we see in that uncertain heating load, in the nighttime period, there's very little cycling needed by the air conditioner because there's less heating load in the room, so we're not actually needing that compressor. So we have that very uncertain time-varying heating load, as well as we have somewhat complex energy characteristics. By turning the compressor on, we have this transient that's produced that consumes more power for a short amount of time, just like any motor would. And we need to consider that in our control algorithm so that we minimize the number of cycles that we're running this compressor, as it's least efficient right in that early stage when it's using a lot of power. I should say that the supply following aspect of this is actually it's somewhat interesting. So it's energy efficient, but essentially what that is it's following a supply that's 0 watts. It's trying to get as close to that 0 watts as possible, so it's changing the operation to kind of follow a null supply. And so what we did in order to model this room, this is more of an advanced controls technique that we employed, is we built a model that was constructed on Newton's law of cooling. So essentially the pieces here are, there's heating from a bunch of different sources. There's the time constant of the room. There's a reflection of the air conditioner and what its behavior is. There's a reflection of the weather and how much solar gain there might be through the two windows. There's two sides of the room that have windows. And then there's this last term, which is the uncertain heating term. And each of these terms has a parameter attached to it, and we identified these parameters using a semi-parametric regression technique. Details can be found in the dissertation. But essentially what the result is that we're able to build a model that's faithful to the operation of the system, as well as what's really nice that comes out of this is because we have knowledge of what these first three terms are in the model that we've produced, we can actually at any point in time pull out the term that reflects this uncertain heating and equipment. So we have, in this bottom graph represents sort of the heating from occupants and equipment. It's a measurement of occupancy that's derived indirectly only from a temperature sensor, which is a very useful thing to have. So some of what we use in order to employ this model is what's called learning-based model predictive control. And this is a technique developed by a colleague, Anil Aswani, in the electrical engineering department. But what we use this model predictive control for is essentially that it's a special variant that uses two different models rather than a single model for its control. And these two different models have different capabilities. One is your performance model, the model that learns and allows you to get better. It can employ any kind of statistical tool to get better, but it's constantly trying to push the boundary and improve performance. As well as, since we have a safety constraint in this room, we have a separate model that's essentially the baseline model that it doesn't change over time with learning. And it represents the constraints. It's, for example, the constraints might be to maintain temperature between this level and this level, or try and maintain supply between this level and this level, or so on. And it doesn't change over time. And so using this learning-based model predictive control technique, we controlled the room for a number of different days. And what's interesting about this room is that it's a living laboratory. This is a room that's in use by students constantly. And so what we're not able to do is do fully controlled experiments where we try with the same inputs and the same inputs using two different control sequences, because the inputs from the weather as well as the inputs from the equipment and the occupants are changing. So what we do to address that is actually we run our two different control scenarios, but at the same time we use the exact same inputs and we use our model to run the opposite scenario. So for example, we run the thermostat controller, but then we simulate the learning-based model predictive control using the exact same input, so we can see how that system would have done in the same scenario. And this is a consideration we had to make because it's a living laboratory, because those inputs are changing. So in both cases, what we did was we ran the thermostat controller and then simulated the learning-based model predictive controller, and then we switched it around, ran the learning-based model predictive controller, and then simulated the thermostat. This occurs on different days, different inputs, different weather. So the results reflect that. What we actually found is that we're able to get quite a bit of energy savings, 30 to 70% energy savings. That's a function of the weather and the usage of the room and everything else. So there's quite a wide range of possible benefit there. But from a supply following context, what this gets you is this is your bleeding edge. This is as efficient as you can possibly be. And so you could, in a supply following context where you're trying to match a supply that's non-zero, you can get as efficient as this. You might be less efficient, but you can this is essentially representing how proportional, how flexible your load, how much slack there actually is in this load. And it's quite a large number, up to 70%. And so now that we've looked at a few different kinds of supply following loads, I want to discuss some other strategies that you might use to improve the match between supply and demand on grids that are highly renewable. So as we noted in the thermal storage refrigerator work, what you're targeting in these cases is no longer the overall load duration curve, but actually just the natural gas curve. And so this is that same load duration curve, again, with its very peak. This is prior to using any supply following load on this. And again, so there's some important characteristics about this curve is that it's very difficult to operate with existing resources. You have pretty massive changes in generation that's expected of the natural gas resources. So we'd like to actually flatten this so that the natural gas resources are used somewhat uniformly and evenly, so that we're not constantly dispatching and making use of that difficult transition. So this is actually a really nice target for optimization. What we're trying to do is flatten this peak up here. And so how might we do that? Well, one, I mentioned earlier, targeted energy efficiency. And so you can imagine that for each kind of electricity load, there's a certain pattern with how it consumes electricity. Likewise, for each kind of generation, there's a certain pattern with how it's been used to provide electricity. And in the case of our 60% grid, there's a certain pattern that falls out for how the natural gas generation is used. And so what I've done here is I've actually taken 13 classes of loads. This is from the California Commercial End Use Survey. So these are all commercial load classes. And I've done a cross-correlation of their time series. So looking at when they consume electricity and compared that to, I've done a cross-correlation with the generation of natural gas. So you essentially, by traversing this x-axis, as you go higher, you get to using loads, you're looking at loads that have more natural gas in their consumption mix. They're consuming more energy generated from natural gas. And as the other axis is just the average load consumption of that class of loads, so you can get an idea of how big these loads are relative to each other. So ideally where you'd like to be focusing your energy efficiency work, where you'll get the most bang for the buck from a perspective of reducing natural gas, is up in this top right corner. So interior lighting, for example, and starting to look at refrigeration and things like that. But what's also important is where you get the least bang for the buck. So all the way over here at the left by itself is cooling. That low correlation reflects what we can intuit from our graph, is that cooling generally occurs during the middle of the day. Well, when we have lots of renewables, we no longer are constrained in the middle of the day. That's we got rid of our cooling crunch. And so we no longer need to focus in this kind of scenario, we don't need to focus our efficiency efforts on cooling. In fact, it makes a lot more sense to focus it in other areas. So another way we can address this mismatch in supply and demand is looking at hydroelectricity. And this is one that I mentioned earlier. But what we can do is modify supply-side resources now that we know how the demand is changing. And so looking at the hydroelectricity in the grid today, it's the largest source of energy storage. It's the largest reservoir of energy storage we have. Essentially what's happening now is that we have lots of these pumped hydro facilities, 4 gigawatts of capacity, where we have reservoirs at different levels in the mountains. We pump water up at nighttime. We release it through turbines during the day to produce electricity at times when it's more expensive. And so our strategy is actually to change that from night to day to times when our use is actually, what we're trying to target now is not overall demand curve, but targeting the natural gas duration curve. And so you can imagine this is what a day looks like in the current grid. Watch the hydro portion, the blue at the bottom here. This is, if we wanted to change it to manage it to better match the natural gas use in a 60% grid, we'd actually shift it quite a bit and push it to times when we no longer have excess. So this peak in demand here and later in the day is a good use of that hydro resource rather than using it in the middle of the day. We can use it at these later hours. Plus, there's some hours in the morning where we're using quite a bit of natural gas. So how does this technique work over the year? Well, this is a chart that shows essentially the yearly contribution of this technique if we applied it on every single day. So it provides over a gigawatt at certain times. But the problem is that the correlation of when this resource is actually available fits in with when our renewable resources tend to be available. So in this winter time, this time when we're using lots of fossil energy, our hydro resource is actually fairly low, and especially our dispatchable resource, that this pump storage, is fairly low. So there isn't much contribution that we can do to alter this problem we have here in the winter where we're using lots of fuels. Whereas in the summer, we have quite a bit of ability to use this. So I want to conclude a little bit and talk about kind of the path forward in this research. And so what I've shown are some initial steps in building supply following loads and evaluating them at grid scale and understanding what their role could be at different levels of on different grids and in different penetration levels. So another thing is that supply following capacity here is increasingly important as you change the consumption, you change the patterns of the grid, as we add renewables, as we fundamentally alter the problem of supply and demand matching. Having these tools at the disposal of grid operators and of consumers is critical to maintaining reliable electricity. It's really important to consider the interplay among these things. I showed that hydro chart at the end, and that's pretty telling that it matters when you apply these strategies and which ones you apply in concert. But the takeaway that's big out of that is that we need all of the above. It's a very difficult problem to make that thermal generation go away, as well as when it's here, use it effectively and appropriately. But we need to use all of these strategies kind of in concert, as well as even more. So thank you all for coming today. I appreciate it, and I'm open for any questions.
Okay, I think we're over time, so I think, if you have any questions, please come up and talk to Jay at the end. Thank you.
Thanks, everybody.